Right. Good morning, everyone. My name is Houge. Very good pronunciation, thank you. I'm from the Globe Institute at the University of Copenhagen, working with Anders Johansen. And in my talk of today, titled Outbursting Objects as Laboratories to Study the Evolution of Dust and Water Ice, I'm going to tell you a story about dust, ice, and fire. So here's a cartoon that I made just for you, showing an icy dust aggregate, icy particle, as we expect in protoplanetary disks. They are typically 1 millimeter to centimeter in size, so not to scale on the screen, of course. But if you zoom a bit closely, you will notice that they are made of smaller grains that we call monomers that are inherited from the interstellar medium, right, for the interstellar cloud. So those monomers, they are typically 0.1 to 1 micron in size. They are consisting of a core of refractories like silicates, iron, and so on, and they are surrounded by a mantle of ices, typically water ice. The thing is, protoplanetary disks are quite an intense, funky environment to live in. So the protostar is evolving, right, on the main sequence. To go to the main sequence, the luminosity is evolving. You can have accretion outbursts. This is the point of my talk, the point of this whole conference. Those icy particles, they can move in disk, up and down in the disk atmosphere. They can drift inward to a region where the temperature increases. So all of that to say that those icy particles, they can experience a variation in temperature throughout their evolution until they are eventually safe into a planet. So sublimation, and here I speak about ice sublimation, is quite a common process that happens quite often in disks. The thing is, I was just showing you on this amazing schematic. Yes, that's monomers. They are stick together, right, to make those aggregates, and they are stuck together by those mantle of ice. So if you sublimate the water ice, what happens on a microscopic level, and how does that impact the aggregates as a whole, like its cohesion, its structure, and so on? So our story, too loud, sorry. Our story begins in 2011. We have this fantastic lab experiments by Omatal and Worm. So they studied this very question. They have icy dust aggregate about 1 millimeter in size, and then they increase the temperature and they see what happens. So you have a picture from the experiment here showing like you have this kind of blob, right? It's like an aggregate. And when the temperature increases, it's breaking apart. So here's just one breaking event. But in the course of the experiments, they noticed that those aggregates, they fall apart in thousands to tens of thousands of subspecies, which basically tell you that aggregates fall apart when they lose their ices. So in the same year, we have a planet formation model. Theorists, Saito and Sirono, they applied those findings to a planet formation model. So they have a 1D disk. So in the outer regions, you have those pebbles, right? So the big grains that drift inward. They're covered in ice because it's in the outer regions. And as they drift inward, they're gonna experience a warming because it's warmer in the inner regions. They're gonna cross the water snowline. And so Saito and Sirono, they implemented the findings from the lab experiments to their planet formation model. Basically, when the pebbles cross the snowline, they release the water and they fall apart. And if this happens, small grains are very well coupled to the gas, so they're gonna accumulate like a traffic jam. You have a big influx of pebbles and everything stays stuck inside the snowline. So it favors planet formation. So I want to here make a little parenthesis that we have a lab experiments finding a new behavior about dust, and it's completely changing where we imagine planets form and what chemical reservoir they are gonna harbor. So I just wanna tell you, like, we need to care about dust a bit more. Unfortunately, lab experiments, as Bob also mentioned, is a bit tricky. We are often finding opposite findings. So Spadacia and collaborators 2 years ago, they did the exact same experiment with a different setup and a different parameter space. And they found, except in this sub case, so this picture shows you the residue after sublimation, that aggregates are very much alive. So they sort of managed to survive sublimation. So we have 2 lab experiments, 2 opposite results. So one I will call the many seeds, everything falls apart. One I will call the resilience, the surviving model, supported by this new experiment, basically saying that on microphysics scale, somehow monomers can rearrange and the aggregate is saved. So how can we solve this sublimation mystery? So of course, Saito and Sirono in their planet formation model, they predicted that we would have a traffic jam effect inside the snowline. So we can just maybe look at the snowline and see if we see a traffic jam effect. This would favor this disruption hypothesis. The thing is that we want to use ALMA to study dust, and we cannot see the snowline. It's too close to the star. So of course, how can we solve this problem? This is the point of this conference, is disks undergoing accretion outburst. So in a disk, undergoing accretion outburst, this is the situation. So in the quiescent phase, Snowline, super close to the star, 1 to 2 AU. During the outburst, super warm. I'm here considering the FUor-type outburst, so the big guys, the strong guys, the one that pushes the snowline to 10 astronomical units and even more than that. And that is quite interesting because everything between the initial snowline and the new snowline, water ice used to be just hanging around and happy, and then it's sublimating. So you have several Earth masses of pure water ice that's sublimating in this whole big region. So we can maybe just study that, right? So before starting with observation, we actually did some model. I'm a theorist at the first place, so we use DustPy. So DustPy is the king of the dust evolution models. So it's those two complicated equations basically together. On the left, you have the small Shosky equation telling you how dust are going to grow and fragment, so how to predict the particle size. And then you have the advection diffusion equation that tells you about the transport of dust. So dust of different sizes, they're going to move differently in the disk. The small one, well coupled to the gas. The big ones are drifting. So taken together, you have a fantastic code that takes 5 days to run, but tells you everything about dust growth, fragmentation, transport, everything you need to know. So we modified, of course, because we want to study FUor-type outburst that we will see after. We are focusing on V883 Ori. So in V883 Ori, we had a talk yesterday by Maho Limker, but also the new data of John Tobin that with direct observation of water vapor teaches us that the snowline, the midplane snowline, is at 80 astronomical units. So we make an outburst with such a strength that the temperature at 80 AU will be 150 Kelvin. So that's how we plug in the strength of the outburst. We have the two simulation scenarios. So we will run one model with the resilience surviving case, one model with the breaking apart. And we are using another finding from lab experiments that's very debated, as Baobab mentioned, is that dry silicates are weaker to fragmentation than ice-rich grains, which means that silicates will grow to smaller sizes. Results for you. This is typical DustPy output. This is before the outburst, right? So on the x-axis, distance to the star. On the y-axis, particle size from micron to centimeter. At 2 AU, is before the outburst, right? We have this vertical dash lines indicating the water snowline. Inside the snowline, grains are small. Outside, they are big because they're more resistant to fragmentation. The most important line of this plot is the blue line. The blue line shows you the fragmentation barrier, and basically that's where particles want to be. If they're below the blue line, they want to coagulate to this blue line. If they're above the blue line, they want to fragment down the blue line. So this is the happy place, let's say. So now we put the outburst first, resilient case. So resilient case, things are surviving. The first thing you will notice when I put this GIF on is that the water snowline will be pushed outward because it's warming up the disk. And you will see the blue line will be shifted down because you are removing the water ice. So things are becoming less resistant to fragmentation. So this is what happens. So grains are surviving. They're pretty big. And you can see here I'm running the model for 10,000 years, which is super unrealistic for an outburst. But it's just to see how long does it take for the grains to adapt. And basically on typical outburst timescale of like 100 years for FUor-type outburst, you can see it's not long enough. Dust is painfully slow to adapt to the new conditions, and they're too big, like they're above the blue lines. In the opposite, many seeds, it's the opposite situation. Everything breaks apart, has to regrow, so it's below the blue line. It's gonna try to go up on the blue line, but it's so slow. So I love that to say that if you are observing a disk, undergoing an accretion outburst, depending on the sublimation scenarios, you can expect extremely different size distribution. So we can just look at the disk and see what happens. So we used V883 Ori, love V883 Ori. So thanks to a lot of effort of people in this room, we have had so much data on V883 Ori, that's fantastic. So I did some new multi-wavelength analysis of V883 Ori based on all those new data, so band 7, band 6, band 4, and band 3, and we are focusing here on the spectral index. So when you take a spectral index, you take the slope of the dust emissions, and you take this by pair of bands. So you have 4 bands, you get 3 spectral index. Up. So you're focusing on the regions where we expect that sublimation happens. What you can see is that they look pretty much similar. So those are new spectral index, right, from those new analyses. So below 10 and 20 AU, it's basically optically thick. So you are below a spectral index of 2. Then we have this kind of transition into an optically thin region. And outside 50 AU, it's optically thin. And you can see the spectral index of basically 2.5, 2.7. So what we did then is to take our super fancy DustPy outputs. Using D-sharp opacities, we can convert those dust size distribution into opacities, then into intensities, and then into spectral indices. So we can compare our dust models with observations. This is comparison with Gemini's model. it's too big. So in Melis's case, grains are too small, so they have higher spectral indices, and it's not good, not a good fit. But now if I show you the resilient case, it's actually quite hard to distinguish the lines. So the point here is not to make a fit, right? Despite it takes 5 days to run, and it's a 40 parameter space thing, I'm not going to do an MCMC to fit those V883 Ori spectral indices. But qualitatively, you can see that to expect those super low spectral indices in V883 Ori, we need grains to resist the sublimation. So, conclusion, the resilient model fits so much better. And it's also highlights with the results from Baobab in FUor-type, right? We find big grains, and the only way to have big grains, and if they survive sublimation. So a couple of implications, the funnier part, let's say. Actually, tens of applications, and I'm super happy to discuss this with any of you after, but I will just make 2. 4 minutes, fantastic. So first, we want to know what about the water snowline, because where we think planet formation happens. So in an outburst, super intense heating, the temperature is multiplied by several factors, even an order of magnitude over a few years. But when pebbles in a quiescent disk are just drifting slowly inward, they're experimenting a warming of basically a Kelvin per year, and actually much lower than that, but super gentle. So if we observe in accretion outbursts dust to be pretty resistant and surviving the sublimation, then well, it's pretty much safe to assume that it's similar in the inner disk. So it's the wrong schematic here, but should be surviving. So pebbles should be resisting there. So this would have implication for planet formation models, right? Because Saito and Sirono found that planet formation is boosted inside the snowline if things fall apart. And I'm finding that it is not falling apart. Sorry for planets. Then second point, and I'm super happy that Baobab spoke about this before, and I'm going to expand on his point. He was speaking about the dry pathway to planetesimals, basically saying that if you form planets during an outburst, you will have dry planetesimals and dry planets. But the thing is, if you have this resilience model, the size distribution is super broad. You have those big guys still hanging around, not fragmented yet. And if you have a broad size distribution, well, after the outburst, when water vapor can condensate back, it's going to do so depending on the surface area of the dust particles. And, well, small grains dominate that. So small grains are going to be pretty damn icy. And pebbles, which are the planetesimals, building blocks, they're going to be pretty ice poor. So this is a plot from my 2023 paper, basically showing you how long does it take once you have this recondensation for the dust to re-equilibrate. Because of course, then you will have a collision between the icy small grains and the dry big grains. And at some point, they're going to go back to the initial conditions. But at 5 AU, it takes 1,000 years. And it's going to scale with distance to the star. So at 10, 20 AU, it can take 10 of thousands of years. So I want to emphasize here that we have an event like an outburst that lasts a year to 100 of years. Is going to have an impact on planet formation for thousands to tens of thousands of years, much longer than the event in itself, which means that we can have a pathway to drive planet formation, not only during the outburst, but well after that. Conclusion for you. We found that the impact of accretion outbursts depends on the sublimation scenarios. We have very different size distributions, but from comparison with V883 Ori, and actually also the data from FUor-type, it seems that dust particles survive sublimation. This has impact for quiescent disk, classic planet formation models, because we can extend our results to area of sublimation where it's a bit more gentle. And I spoke about the water snowline in a quiescent disk, but you can imagine that for any sublimation you like. This kind of going accretion outburst can lead to the formation of dry planetesimals extremely long after the outburst has ended. So imagine a young star with a lot of outbursts. Well, I really don't know how we are going to make wet planetesimals in this context. Yeah, and the last conclusion, I don't have too much time, so I will stop here. So thank you for listening to me. It was a pleasure, and I will take your questions now. Thank you.
Thank you very much. Agonish.
Thank you. Very nice results. So I'm curious about one thing. One interesting result when we checked the 10 micron silicate feature of FUors was that most of them have this very broad trapezoidal shaped silicate feature, which indicates grown dust, as opposed to if you look at T-Tauri stars, you see a wide variety of 10 micron features from the grown to the pristine ISM-like feature. So can you comment on what the implications of these models would be for the 10 micron silicate feature?
Good point. So I'm not an observer. It's a tricky question for me. Well, in the light of those results here, I'm not sure it would have actually a great impact, because when you have the fragmentation of big pebbles, they're going to make any small grains you want, right? So they're also going to make 10 microns dust. The only way I could see that an outburst could impact the 10 micron features is maybe if, thanks to those warmer temperature, they can grow those small grains that are powered by Brownian motions. This is going to be much faster. So I would expect the super small grains, like the 0.1, 1 micron, 10 micron grains, to have a boosted growth thanks to the growth of the outburst, and thanks to the temperature of the outburst. Hence, you may lose this 10 micron features thanks to that. This would be my idea.
Okay, yeah, go ahead. Next question is Fernando or no? Oh, go ahead.
Hi, thanks for the very nice talk. So there has been a study on the bouncing barrier. I think Dominic Dulemon 2023, they show that actually bouncing barrier happens earlier than the fragmentation barrier, which is disappointing. So, but I don't think that you take the bouncing barrier into account in your dust pi model. So do you have any comments on this?
Yeah, so of course, yes, coagulation and fragmentation. Actually, lab experiments didn't even find just bouncing, they actually find tens of different outcomes to collisions, so it's impossible to put them all together. But bouncing is indeed a good one. Quite a lot of people think it exists. We didn't take this into account, but if it does happen before fragmentation, it means you will have smaller grains. They cannot reach bigger sizes. The problem with that is that in V883 now with those new fantastic spectral indices, and it's quite low. And to reach such low spectral index, you need quite big grains. So the bouncing barrier could be a thing, but it should happen a bit later maybe. So I didn't implement this result, but it could be fantastic if someone would do it. If you would like to do it, I think it's we need to explore a bit more this bouncing. So I don't think it would work for V883, but I think it would be worth investigating, yes. Thank you for the question. I think, Sergey, you had a question?
Thank you. Yeah, really interesting results. But
Okay. What happened to everyone? No worries.
But you are doing this calculation still in 1D, of course. And as I mentioned, we should be suspicious of 1D codes. I don't quite trust myself with some of 1D stuff. You have a heating wave propagating through your disk, right? And what this will do is your disk will puff up gradually, right, as a function of radius. And so there's going to be sloshing of material back and forward, and also, up and down like this. And it's not clear to me if that will not induce sufficiently strong gas motions that might start, bumping dust grains against one another. And, that can be quite a significant effect. So I think we need to be a little bit cautious about these effects that are still not in the 1D treatment.
No, I definitely agree. I think one of the things at the moment is that in the outbursting community, we have sort of two types of modelers. There's people doing chemistry and just like me who are using quite a simplistic approach for how the outburst propagates. So we typically use step-like function. As we said yesterday, we just assume the star is more bright. Then we have all those fantastic results from you guys with those 2D, 3D models, non-MHD, ideal thing. I don't know quite much about. I think this is the next step is yet to try to implement more fancy light curve in this propagation wave of heating. But at the moment, dust pi already take 5 days to run, and I'm not aware of any dust evolution codes that will ever be published soon, actually, that could implement this. But I agree that having this kind of heat wave propagating would be something fantastic to have. Also something that I've been thinking, because now, basically, we have the structure in the intensity map of V883, right, at 42 AU, that used to be associated with the water snowline. But now we have those new spectral indices, and there's not much going on at 42 AU. So the only reason I'm thinking to explain this annulus now is something linked to the temperature. So it would be fantastic one day to have a better temperature estimate of what's going on in V883 with viscous heating, with latent heat, all those things taken together. So yeah, next steps for sure.
Okay, so thanks again,
Thank you,
Adrian.